Okay, so for today, for lab, you're going to do the effects of exercise on heart rate and blood pressure and the effects of body position on heart rate and blood pressure. Let me see if I can get my little pen up. Um, okay, so first off, what we're interested in is typically if we were on site, we would use the oscillatory method to determine the response of the cardiovascular system to body positions and exercise. Os- Oscillatory method is listening, and so you would use a stethoscope and a blood pressure cuff um, to listen to your heart rate and blood pressure. Okay. Um, I want you to uh, go to the virtual lab at McGill University in Canada and read how to take blood pressure and heart rate. And then there's useful links at the bottom. So click on this link and go through it. Since do, we can't take blood pressure in lab, um, and that's something important that you should know how to do. And then there's info on blood pressure and heart rate at this clinical site for UCSD med school. So go ahead and look those over, read them. You can read the introduction of this. The first thing that we would do if we were in class is we would listen to the heart sounds. So when you listen to the heart, you typically hear a lub dub sound, right? And that is pretty much common knowledge. Where do we get that lub dub sound? So we get that, let me page down here. So we get that lub dub sound from the closing of the atrioventricular valves and the closing of the semilunar valves. So the first sound that you hear is actually the lub, right? That is caused by blood hitting the atrioventricular valves when they're closed. Now, it's not actually the valves closing that make that sound. It is the AV or atrioventricular valves closed and the blood hits them. So that you can hear with the stethoscope. The second heart sound is a dub or dub, however you want to say it. That is caused by the closure of the semilunar valves. So it's actually the semilunar valves being closed and blood hitting those. And so typically we would listen to the heart sounds first, the lub and dub. You're going to hear the lub at the in between the fifth and sixth intercostal space, and then the dub in between the second and third a rib in that intercostal space on the left hand side. We do this first because this is louder than hearing the blood pressure sounds through the stethoscope. Okay, so if you look at auscultation of heart sounds, you're going to hear the lub, excuse me, the lub down here and then the dub up there, right? Then we would move on to figuring out pulse rate and blood pressure, right? So pulse rate, obviously we've taken pulse rate before in lab, but just to reiterate, it's your index and middle finger. You're going to press against your radial artery, against your radius, and you're going to count the pulses for 30 seconds and multiply by 2, or you can do 15 seconds and multiply by 4 to get your beats per minute. I want to talk a second about blood pressure. So normally we would take blood pressure. What is typical blood pressure measurement? So typical blood pressure measurement is, and I'm going to try to write it on the side. So typical blood pressure measurement is like 110 over 70 or 120 over 80. What's the unit of measurement? It's millimeters of mercury. So that 110, right? What does that denote? Is that what pressure is that? Good. So this is your systolic blood pressure. And the 70, the bottom number is actually your diastolic blood pressure. What is systolic blood pressure? So systolic blood pressure is the pressure in the arteries and arterioles, and you can say this is in the aorta when the heart contracts or when that left ventricle contracts. So systolic blood pressure is a pressure in the aorta when the left ventricle contracts, right? um, you remember learning, we labeled systole. So we talked about systole for cardiac cycle, and we talked about measuring systole, the time it takes for systole during the EKG, right? So your P to T interval is analogous to systole. That's when the heart's contracting. And so when the heart's contracting, we call that systole, and that gives rise to your systolic blood pressure. The bottom number is diastolic blood pressure. That is when your heart's at rest. So it's a pressure in the arteries when the heart's at rest. Remember, there's pressure in the arteries because our circulatory system is a closed system and there's blood volume. And so anytime you have a closed system with fluid, you're going to have an inherent pressure in that system. Okay, so we can use these two numbers. So we want to look at systolic blood pressure and diastolic blood pressure for a patient, but we also want to be able to calculate it. And so let me go over the calculation first, and then I want to go over the theory behind it. So the calculated MAP, why do we want to calculate your mean arterial blood pressure? So to calculate MAP, it is, let's write it over here, diastolic pressure plus 1/3. And there's another way to learn this. If you know the other way, that's fine. Diastolic pressure plus 1/3 systolic pressure minus diastolic blood pressure. Okay, this is actually pulse pressure. So what this ends up being is, let me change the color. Let's do blue. Our diastolic blood pressure is what? Good, that's 70, right? And then systolic minus diastolic, so this would be 110. Let me write it for you guys. Whoops. Let me erase it. My pencil went crazy. Holy cow. Okay, let's try this again. Okay. Oh, let's do that. Okay, so it's 70 plus 1/3 of your pulse pressure, and pulse pressure is 110 minus 70, which is what? Good. So 70, or excuse me, it's going to end up being 40. So let's erase this. Sorry, you guys. I'm making a mess of it. Oh no, I totally lost it. Okay, let's, I guess I'll just rewrite it over. Okay, so let's try it again. So it's diastolic pressure plus 1/3 systolic minus diastolic blood pressure. Okay, and this ends up being systolic is 110, diastolic is 70, so that ends up being 40, right? So this is 1/3 of 40, so 40 divided by 3 plus 70 ends up being like 83 for your MAP. So MAP usually, and it's in millimeters of mercury, right? MAP usually ends up being, a normal MAP range is around 80 to 100, 110. right? Why is this important? Your heart has to generate enough force to get blood flow to your body. Your MAP has to be greater than or equal 55 millimeters of mercury to get blood flow to organs, okay? If your heart, if your left ventricle can't contract with enough force to get MAP to be greater than 55 millimeters of mercury, you're not going to get blood to your organs. And so your organs are going to go through failure. They're going to shut down. And so regarding patient care, this is really important. Clinically speaking, my father had sepsis. He had a blood infection and his blood pressure dropped. And so the first thing that they did was that they raised his feet above his heart. And so they caused more blood to return to the heart. And that helped a little bit, but not much. They ended up giving him some epinephrine, and that didn't do much. And then they gave him a potent vasoconstrictor, and that vasoconstrictor constricted his blood vessels right up. And so at the lowest point, his MAP was around 40 millimeters of mercury. And he was still conscious, but he was fading. And so they gave him a bunch of different chemicals to get MAP up so that he wouldn't be in systemic wide organ failure. Okay, so I'm going to erase this, and then I want to go over the theory. Okay, so let's just erase this whole thing. Let's see if that works. So the theory behind this, MAP, whoops, see, there you go. So your mean arterial pressure is dependent on your cardiac output times your total peripheral resistance. So when you think of mean arterial pressure or blood pressure, you should think of what the heart is doing, which is your cardiac output, and what the blood vessels are doing. So that's your total peripheral resistance. So cardiac output is dependent on, and we'll cover this in lecture, heart rate times stroke volume. Heart rate is in beats, right, per minute. And then stroke volume is volume ejected from that left ventricle per contraction of that left ventricle. So how much blood is that left ventricle kicking out per beat? So if you look at this mathematically, what can you cancel out? Okay, you can cancel out beats, right? So I'm going to put a line through that and put a line through that. So what do we have for cardiac output? Cardiac output is the volume of blood you eject from the heart per minute. And so usually if you think of beats per minute as 70 beats per minute, right, average heart rate, and then stroke volume is 70 mils per beat. You get 70 times 70 is 4,900 mils per minute, or 4.9 liters per minute. So basically it's your entire blood volume, about 5 liters of blood circulating or kicked out from the heart per minute. So that's a lot of blood, right? Your total peripheral resistance is the resistance of your blood vessels. Okay. The resistance of the blood vessels can change depending on how much epi and norepi you're releasing, right? Keep in mind that they don't have acetylcholine receptors. They don't have nicotinic cholinergic receptors or muscarinic cholinergic receptors. So they respond to epi and norepi. So if we want to increase resistance because we want MAP to go up, you're going to do what? So how do we increase resistance? We are going to vasoconstrict those blood vessels, right? So when we make the diameter smaller, we have the same volume of blood, resistance is going to go up. And so blood pressure is going to go up systemically. What happens? How do we get a decrease in resistance? So decrease resistance, that, good, we're going to what? We're going to make the space bigger for those blood vessels, so we're going to vasodilate them. Good. Okay. And so when you vasodilate the blood vessels, you open up, resistance drops, and so MAP is going to drop. So there are two ways that we can regulate pressure. We can increase cardiac output to increase pressure, or we can increase resistance by constricting the blood vessels systemically, and MAP's going to go up. Or we can drop both of these. Now, if blood pressure is low, you're going to do both of these. If blood pressure is high and you need to bring it back down, you're going to do both of these as well. You need to think about how different body positions affect that, right? So if you are standing up, blood is pooling at the feet because we live on planet Earth and we have gravity. So blood's pooling at the feet, and so you're getting less venous return. Less venous return is going to affect which variable? And when I say less venous return, I mean less blood flow back to the heart. So it is going to affect which one? Good. So it's going to affect your stroke volume. So less blood back to the heart. Whoops. Less blood back to the heart, less venous return, less stretch of the myocardium, and then less stretch of the myocardium, less stroke volume, right? So that's how you need to think about it. I wish these would just go away. Let's see. Let's do the green color, the dark green, so you guys can actually see it. Okay. So what happens then when you stand up? So when you stand up, does stroke volume increase or decrease? Or no, let's say lay down. So when you lay down, your feet are at the same level as your heart. And so blood is going to go back to the heart, or more blood's going to go back to the heart. And so you're increasing venous return, and that's going to increase stroke volume. And because you increase stroke volume, that's going to increase cardiac output, and that's going to increase MAP. All right. And so body positions, you want to think of those body positions as the stimulus for your whole feedback loop, right? So if you have an elderly patient and they're laying in the bed, are they going to just jump right out of bed? No, because their blood pressure is going to tank, right? So you're going to have them sit up first and let their body adjust to the homeostatic feedback loop, right? Or using their homeostatic feedback loop. And then you're going to have them stand up and let them adjust as well. And so what ends up happening is when you stand, MAP's going to drop. And then you're going to go through your homeostatic feedback loop to regulate it. When you lie down, MAP goes up. It's going to go up, but then your homeostatic feedback looper is going to bring these guys down or adjust these guys to bring this down, right? So when you lay down to go to bed at night, because you're laying down, blood pressure goes up. There's more venous return, greater stroke, stretch of the myocardium, greater stroke volume, greater cardiac output, greater MAP or blood pressure. But then as you're laying down at night, your blood pressure drops, right? So your blood vessels dilate, cardiac output decreases, and MAP's going to drop. And in fact, it drops, and it's the lowest, not quite right before you wake up, but it gets lower. And then when you wake up, obviously it goes up. So your body has its own sort of set point or regulatory set point as you're sleeping. So let's look at how we regulate it, okay? Skip forward, and I want you to read all this because this is important. Orthostatic blood pressure changes means body position. So when you're sitting, standing, or laying down, how does that affect blood pressure? That's important. And then we're going to do effective exercise on blood pressure and pulse rate. Okay, so let's look at your laboratory report. The first thing, that I want you guys to do is fill in your homeostatic feedback loop for blood pressure, right? So when you lie down, what happens to blood pressure? Good, more blood back to the heart, so blood pressure is going to go up. So that is your stimulus. So whatever body position you're in and that causes an increase or decrease in blood pressure, that's going to be your starting point, because your body is always evaluating blood pressure. And when you change body positions, that is going to be monitored by your sensors, right? So I want you to figure out what the sensors are. So are they chemoreceptors? Are they osmoreceptors, thermoreceptors, baroreceptors? And give me locations for those. We talked about those in lecture, or we're going to talk about those in lecture. And so they're in the PowerPoint. The integrator, is it medulla oblongata or hypothalamus? Good, it's going to be the medulla oblongata. So it's going to measure it against a set point, and then it's going to send a signal out. So if blood pressure, the stimulus was an increase in blood pressure, you're ultimately going to have a drop in blood pressure. Okay, what are the effectors? You have two effectors. It's going to be your heart and your blood vessels. And so that's important. And remember, if you give me two effectors, I want you to give me if you give me two effectors, I want you to give me two responses. So what does your heart do? It's going to do something with cardiac output, and your arteries are going to do something with resistance. So it's a lot like the MAP equation, it's just more drawn out. Okay, and so by the time you're done, you should have a decrease in blood pressure. All right, keep in mind your heart is going to drop cardiac output, and part of that is heart rate. So if you lie down, blood pressure is going to jump up, but then as your body regulates it, you're going to see heart rate drop. And that confuses students right away because they're like, oh, blood pressure is high. Why is heart rate dropping? Well, your cardiac output's dropping and your arteries are dilating, and it takes a little bit of time for blood pressure to drop too, but it'll follow suit. Everybody's a little bit different on how fast their nervous system reacts to this. Okay, so how would blood pressure and pulse rate change for standing versus lying down if you had to make a prediction? So I want you to write a complete sentence, please, of what you think would happen. So what happens when you lie down versus standing, or standing versus lying down, either or? What happens to them? Okay, so if we were in lab, I would have you guys start out by lying down and taking your systolic and diastolic blood pressure, and then your pulse rate. And then I want you to calculate the MAP. And then you would sit up, take blood pressure and pulse rate, and then you would stand, take blood pressure and pulse rate. Okay. I want you to calculate the MAP for those, and then I want you to tell me or interpret the data, right? So when was blood pressure the lowest and pulse rate? When was blood pressure and pulse rate the highest? Does that agree with, or does that support what you predicted, or the sentence, the educated guess, the hypothesis that you just made a little bit ago? Why or why not, right? And then what is the equation used to calculate MAP? For calculating it, not the theory, but for calculating it. And why is that important to know regarding patient care? The second part of this experiment then would be exercise. And so what I have students do is I have them take baseline values. So this is resting, right? So this is the first 5 minutes is resting. So to get baseline values, so let me explain this. So you would take pulse rate and blood pressure for 5 minutes of rest. Let's try that again. Okay. Evaluating it every minute for 5 minutes of rest. Okay, so here's some data, systolic, diastolic, and then heart rate. Then you'd have one of your group members go and exercise and take blood pressure and heart rate while you're exercising. And so here's 1 minute of exercise, 2, 3, 4, 5 minutes of exercise. So this is exercise, right? And this is blood pressure and heart rate for exercising. And then after 5 minutes of exercise, they would stop exercising, and you would take their blood pressure and heart rate while they're recovering. Okay, so this is your 5 minutes of recovering. So then, and I want you to do this at home, I want you to make a graph for systolic blood pressure and diastolic blood pressure versus time. And for time, you can use 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, and then do 6, 7, 8, 9, 10, all the way for 15 minutes worth of data. And so it's going to be systolic and diastolic. So these are your pressure measurements versus time, and you're going to have 15 minutes of time. Differentiate whether you're talking about rest or exercise or recovery. And when you graph it that way, instead of, because people make all sorts of funky graphs, right? So this is time, and this would be 0, right, through 15. And so, and this would be blood pressure. And so what you see is when you graph systolic and diastolic this way, you see the trends really easily. It's obvious to see what happens during rest, exercise, and recovery. And then you're going to do another one for heart rate. Once you have the data graphed, then you're going to answer some questions. Okay, so obviously number 6, but number 7, after you've collected your data, construct 2 graphs, one for blood pressure, one for heart rate. What trends do you see? So what happens when somebody exercises and when they stop exercising? And then if somebody's out of shape, how do you think that affects these trends? So what we end up seeing for somebody who's out of shape, typically when you are fit, let's go back to your, I think you erased it, but let me check. We'll go back to the first equation, the MAP equals cardiac output times resistance. Okay, so when you are fit, your stroke volume, because your heart's a muscle and you are cardiovascularly fit, you've conditioned it. So it's going to, it's a conditioned muscle. So your stroke volume is going to increase, right? So your heart doesn't have to work as hard. You don't have to increase heart rate. You actually increase stroke volume when you're fit. And so heart rate's going to be lower, resting heart rate's going to be much lower because you're ejecting more blood per beat. Compare that to somebody who is unfit. Their stroke volume is not great because their heart is not conditioned. And so the only thing that they can do is increase heart rate. So if you're unfit, heart rate will jump up way higher because your stroke volume can't. And so you'll end up seeing a higher heart rate, higher blood pressure versus someone who is fit. If you go back to the graph, if you look at your graph, if somebody is fit, when they start exercising, oops, sorry, let's try that again. Okay, let's do the green one. So when they start exercising or at rest, you know, here's somebody who's fit, they start exercising, their blood pressure is going to go up, but it's not going to go up that high. And as soon as they stop, it's going to recover. They're going to recover super quick because they're used to doing that. Somebody who is not fit, they're going to have a higher resting blood pressure, and heart rate. When they exercise or start to exercise, it's going to jump up higher, right? And it's going to keep creeping up. And then when they stop exercising, it's going to take, that heart is going to take a really long time to recover. Okay, I can tell how cardiovascularly fit I am by how quickly my heart recovers when I stop exercising. All right. Number 8, what neurotransmitters are responsible for increasing and decreasing heart rate? I'm talking about neurotransmitters, not the hormones. So let me know how you increase, decrease heart rate and how that affects blood pressure. Artery and vein on a histological slide. So I want you to tell me what the 3 layers are, what they're composed of, and what are the function of those 3 layers for the arteries and veins. Okay, guys, email me if you have any questions. Thanks.